Now, up until this point, we've been talking about alkanes, alkenes. Both of those are very, very non-polar, very low intermolecular forces. We're going to find the alcohols, particularly, are the opposite. They have very strong intermolecular forces. They have hydrogen bonding. They have dipole-dipole interactions. They're very strong. Okay. Now, an alcohol is an OH group. Most people, when they hear the word alcohol, they think of drinking alcohol, but there are hundreds of thousands of different kinds of alcohols. Cholesterol, for example, is an alcohol. Sugars are alcohols. Carbohydrates, alcohols. Lots and lots and lots of alcohols. An alcohol is defined as having a functional group of an OH. That's called a hydroxyl group. Excuse me. Now, normally a alcohol has got something attached to it, but it is the functional group. So whenever you're looking at the backbone, make sure the OH is on the backbone. Otherwise, it's not a legal backbone. An ether is similar, only instead of an OH, it's an OC. So an ether is going to be COC. An alcohol will be COH. A special kind of alcohol called phenol. You've probably heard of that. It's frequently used as a disinfectant. A phenol has got a benzene group attached to it. Now, what makes phenol different than the other alcohols? It's a weak acid. And I'm going to get to that in a little while here, but that's what makes it very, very different than a normal alcohol. Okay, now we're going to be using this R designation a lot. R means carbon something. It's a generic carbon group. Notice on the ether we have R and R prime. R prime is different than R. It could be the same. In our class, it's mostly going to be the same, but it doesn't necessarily have to be the same. Now, ethers are very, very biologically common. So are alcohols, as I mentioned earlier. This is the one that most people are familiar with. Eth meaning two carbons, all meaning an alcohol. I'm going to get into naming it as well. Menthol. Do they still have menthol cigarettes? My mother used to smoke menthol cigarettes for years and years and years. That's the only reason I know about menthol cigarettes. Cholesterol. Everyone's heard of cholesterol. Also a alcohol. So if it has an OH group on it, there's a chance that it's called an alcohol. Now, if we look at glucose, a lot of people will call that a polyol. This is in Unit 2. We're going to study glucose extensively. And the reason why it's not called a polyol is because it's got that, this group right here. That's what makes it not a polyol. Now, polyols are used frequently for sugar substitutes, and they're not particularly good for you. Now, ethanol is one of the few alcohols that will not kill you. Will not kill you. Methanol will kill you. Okay, if you buy illegal alcohol, they call it lightning, white lightning, grain alcohol. All those that are not commercial contain methanol, because the distillation process will bring over not only ethanol, but methanol as well. During World War II, a lot of submariners were blind. The reason why they were blind is because they used to, in the torpedo gyroscope, is sitting in a bath of methanol. And the sailors found that if they drink that torpedo juice, quote unquote, they get drunk. Oh yeah, they got drunk. And they also got blind. So alcohols in general are very poisonous, which leads you to believe, then what about carbohydrates? Since carbohydrates have a lot of OH groups. And yes, carbohydrates are also not good for you for the same reason. That OH group, not good stuff. Okay. Okay, so naming alcohols is pretty much like naming an alkene. Okay. Step one, like always, backbone, carbon backbone that includes the functional group. In this case, it's going to be that there. Or that. Either one of those are legal carbon backbones. Both of them contain functional group. Okay, so let's use the yellow one and let's name that guy. Okay, so it's like all the other naming in 3 parts. Parts 2 and 3 are required. Part 1 is optional, depending on if there's any branching. Okay, so we've got 1, 2, 3, 4, 5, 6. Okay, and the functional group is an alcohol, which is an OL. And we've got 2 ways to name this or number this: left to right, right to left. If we start on the right, we'll get lower numbers for the OH group. Now notice I'm not considering the branch in the numbering, only with alkanes. With alcohols, we just considered looking at OH on the backbone only. That determines the numbering. We want the lowest numbering. So if we start here, it's number 3. If we start on the other side, it's 1, 2, 3, 4. So 3 is lower than 4. So it's going to be 3-hexanol, and we have a branch on carbon 1, 2, 3, 4, 5. So 3-methyl, 3-hexanol. You also have 2 alcohols, 3 alcohols. So it would be a diol or a triol. In our class, we're mostly going to be dealing with single ones, though. Okay, so this falls very consistently with naming of alkenes and alkenes. Now we're going to this and using the IUPAC, the official name for naming. Okay, are there any questions about how I name that? We also have cyclic alcohols. Okay, so let's do a cyclic alcohol here. All right, so let's name that. Automatically, the ring structure is the backbone, and that's 6 carbons. So the best way to number is with a functional group being carbon number 1. And then we have an ethyl branch on carbon number 3. So it's going to be cyclohexanol. Now it's optional to put 1 here if you want, just to be consistent. Frequently people don't put the 1 in, but it's totally fine to put the 1 in. And we've got a branch at carbon number 3. So 3-methyl cyclohexanol. Cyclohexanol is a very common alcohol. 6-membered rings are the most stable of all the rings. So you'll see those being most common. 5-carbon rings are also common, but not as stable as 6-carbon rings. Yeah.
Correct me if I'm wrong. Isn't that methyl? Methyl?
It is ethyl. Absolutely. Thanks for pointing that out. I'm so used to doing methyl. Okay, so now whenever we have a benzene ring, like I was saying earlier, we have a special kind of alcohol. And it has to do with the stability of that benzene ring. Benzene ring adds lots of stability to a structure. I'm not exaggerating not even a little bit. It has a whole bunch of stability to that ring. So when we look at phenol, let me back up a second here. So one of the definitions of an acid is it disassociates an H plus ion. So if there's H present in organic molecules, there's a whole bunch of H's, as you know. But if one of them should disassociate as the ion, it's considered an acid. And normally, organic acids are weak acids. So, in general, alcohols are not acids, except phenol. And the reason why it is an acid is because of the stability that this is kind of, if we look at it right. that charge, this is called a conjugate base. The charge on the conjugate base of that acid is spread out over the ring. And that's what leads to the stability of phenol. It doesn't matter if they're one ring, two rings, or three rings, they all add stability. Now, it's called an aromatic alcohol. Now, you're going to find biologically, benzene rings are all over the place in our bodies because they're so stable. Non-benzene rings, six-membered ring particularly, are also all over our bodies. They're not as stable as benzene, but they're still stable. So this makes phenol very special among alcohols. Because of the stability of the benzene ring, it allows that H to come off and become an acid. Okay, let's see here. So whenever we have a base phenol, that's going to be what we name products based on, is that base phenol. So that's going to be carbon number 1, 2, 3, 4. So this is why it's going to be 4-bromophenol. Some people pronounce it phenol with a long E, others pronounce it a short E as in phenol. Does anyone work in a clinical situation where they use phenol? I'm surprised. Usually I have a couple, 3 people that usually work in a clinical situation. Okay. All right. Now, there are 3 different kinds of alcohols. It's called primary, secondary, tertiary. And it's crucial you understand the difference, because that comes into play when we talk about reactions. Primary alcohols react differently than secondary, which act differently than tertiary alcohols. And it has to do with how many hydrogens are next to the carbon that has the OH. Now, we're going to talk a little in a minute about oxidation and reduction. I don't know if you remember that from 305. We're going to talk about it. And that has to do with the ability for a hydrogen to be lost. So if there's no hydrogen to be lost, it cannot be oxidized. So you should be able to get some practice at naming alcohols and then determining whether they're primary, secondary, or tertiary. Now we get into nitrogens, amines, we're going to have the same thing, primary, secondary, tertiary, and quaternary with nitrogen, even more involved. Okay. So we'll get into reactions. This has to do with oxidation properties of the alcohols. Primary alcohols are the easiest. Secondary are hard. Tertiary don't oxidize at all. Now, okay, so that's ethanol. How many hydrogens are here? 2. That means that's a primary alcohol. So when we oxidize a primary alcohol, what happens is it needs an H attached to that carbon that's attached to the OH. And each time it oxidizes, it requires a hydrogen. So if it's a primary alcohol, it can be oxidized twice. So first it goes to something called an aldehyde, which is unit 2. And then it's further oxidized to an acid. So until we get to unit 2 or unit 3, all you need to say is aldehyde, you don't have to name it. Now, this reaction with ethanol is particularly important biologically. When you drink a cocktail, alcohol gets changed in your liver. It gets oxidized in your liver by an enzyme called alcohol dehydrogenase. What it does, it converts it to the aldehyde. There's another enzyme in your liver called aldehyde dehydrogenase, which converts it to an acid, and this ends up being acetic acid or vinegar. We pee it away. That's how your body detoxifies ethanol. The problem is enzymes. How many of those enzymes are present in your liver? That'll determine how much alcohol you can detoxify. That's where they get the term for every shot, every ounce and a half of 50 proof alcohol, it takes an hour and a half to get through your system. 3 drinks, 4.5 hours. 4.5. And that'll put you under the 0.8. There's a 0.08. 0.08. Now, when you take a breathalyzer, you're stopped, you can't walk, doctor, you need to take this test, breathalyzer. What the breathalyzer does, it does this reaction. It changes color based on how much aldehyde is present. Lots of aldehyde, deep color, and that's calibrated to whatever your blood alcohol level is. The other way is at the hospital ER, they'll take a blood sample, do a test there. Okay? So that's the whole thing on ethanol in your body. I was on a jury once, and the judge asked me what my profession was. So I'm a professor. Instead of what? Chemistry. You know how breathalyzers work? I go, I do. He said, do you know how to beat it? I said, yes. And the defense attorney immediately dismissed me. Remember the old Listerine? That was half alcohol. If you gargle with that, you get stopped, you gargle with that, spit it out, you will be way over. And there's no way to tell what caused the alcohol issue in your body. Is it the Listerine or is it the liquor you've been drinking? And that's where you can kind of, it's not crystal clear. The judge did not like the fact that I mean, any chemist don't publish work. It's not like this. Okay, so bottom line is oxidation of an alcohol requires an H. So we have one H here. Zero H is there. So primary alcohols can be oxidized twice. First to the aldehyde, then to the acid. Now, if we look at our reaction flow chart, here we have oxidation. And it says loss of hydrogen. You can also reduce this stuff as well, with oxidation and reduction. As far as oxidation is concerned, we'll do unit one. Okay, so if it's primary, first it gets oxidized to the aldehyde, then further oxidation gets oxidized to the acid. Now, if you only have one hydrogen, it can only be oxidized once. So it goes from the secondary alcohol to the ketone. Tertiary alcohol has no hydrogens, so you react. So when you do your first wet lab on alcohol, you're going to be using a flow chart similar to this. And you can have an unknown. And you determine what's in your unknown. And one of the tests is going to be oxidation. Okay, so let's go back up here again and talk some more about this. Okay, so if we have isopropyl alcohol, it only has one hydrogen. That's right here. That means it can only be oxidized once. And what happens is it goes to the ketone. Carbon backbone is the same. 3, 3, 3, 3, 2, 2. The backbone remains the same. It's just the state of the oxygen changes. So OH. Now, in organic chemistry, instead of talking about electrons like you did in 305 in oxidation, we're talking about H's instead. When you lose H's, oxidation. When you gain H's, reduction. So here we lost an H off that O, and that means that oxidized the ketone. Now, how many hydrogens are left? How many hydrogens? 0. Because we had 1 to start with, and once it's oxidized, we lose that 1. We're left with none. That's why you cannot oxidize a ketone. No hydrogens there on that carbon. And if we have a tertiary alcohol, like that, where we have no hydrogens, cannot be oxidized. Okay, you also need to know the names of these enzymes as we go. So this is going to be alcohol dehydrogenase. Dehydrogenase means pull off an H. It means to oxidize. Enzymes always end in the ASE if they're a modern name. The old ones don't have an ASE. So alcohol dehydrogenase enzyme will work on an alcohol. converted to aldehyde. The aldehyde version is called aldehyde dehydrogenase. The aldehyde dehydrogenase will take it to the acid. Now your body, again, your liver has an X amount number of these enzymes. Guess what kills these enzymes? Alcohol. That's right. Drinking alcohol reduces the capacity of your liver to detoxify alcohol. Who's heard of cirrhosis of the liver? A couple of them, okay? Cirrhosis means your liver is basically, parts of it are non-functional. And the parts that are non-functional are alcohol and aldehyde dehydrogenase enzymes. Additionally, certain cultures have more of these enzymes present in their liver than others. Scandinavia, Russia, Northern European countries, populations have a lot of these enzymes in their liver. That means they can tolerate liquor better than people from, for example, Samoa, for example, some of the islands. Just because they've been drinking for so many millennia, it's kind of weeded out the people that don't have very many enzymes. So the only ones left are the ones that have strong enzymes and they can tolerate drinking more. Okay, does that make sense on the alcohol oxidative potential? Okay, so you need to know these enzymes. We're going to get to these. Yeah. Still in alcohol. But we can't go any further because there's no inches here. There's 0 left. That means it can't go any further. So there's no ketone dehydrogenase enzyme. Because it cannot, ketones can't be oxidized. That's why the enzyme doesn't exist. Okay. All right. IMF. Okay. In 305, you covered intermolecular forces. I don't know if you remember them or not, but there are 3 basic intermolecular forces. Okay, the strongest one is hydrogen bonding. That is where H bonds to nitrogen, oxygen, or fluorine. Enough. If that's so, that's the strongest intermolecular force. Now, the difference between inter and intra. Inter is between molecules. Intra is within the molecule. Now I'm talking about between molecules. Okay, so the stronger one is hydrogen bonding. Alcohols, guess what, have hydrogen bonding. The next one is dipole-dipole. This is Dipole are weaker than hydrogen bonding. And then lastly, we have London dispersion forces, or LDFs. All molecules have London dispersion forces. Sometimes it's just called dispersion forces, and those are the weakest. Alkenes have that. No dipole, no hydrogen bonding. So their interaction between each other is weak. Alcohols have hydrogen bonding and dipole. Now they're going to be the strongest till we get to acids. Acids are even stronger yet. So, what does that mean? That means things that have OHs on them tend to be stickier because the intermolecular forces are strong. We want to bind and attract one another. So when you're trying to boil something, what does boiling mean? Boiling means you pull apart the molecules and get them in a gas. So if they're sticky, they're going to be harder to pull apart and require more energy, higher temperatures to pull them apart. So alcohols have a higher boiling point than comparable alkanes. Alkanes don't have that stickiness of hydrogen bonding like alcohols do. Okay. Now we're going to find this trend throughout this course. Every test is going to have IMFs. Every test is going to have naming, structure. Every test is going to have reactions. No exceptions. Every single test. So I may ask you, for example, list in ascending order boiling points. These molecules. Okay, the top one is an alkane. That's propane. Propane does not have any strong dipole, and no oxygen around. Oxygen is the key, by the way. Whenever oxygen's around, red flag. Look at if there's an OH there or no OH. Okay? Alkanes, no oxygen. Propanol, oxygen. Not only an oxygen and an hydrogen attached to it. So, as we go down, increasing boiling point. Because there's more and more intermolecular forces at play. If we had an acid here, it would be stronger. And that's unit. Okay, now along with boiling point is surface tension. Surface tension is how sticky the surface is. The higher the IMS, the stickier the surface is. Now, if we look at something like water, Water is incredibly sticky because it's got not only one OH group, it's got two OH groups. Two oxygens or two hydrogens participating in hydrogen bonding. So water is incredibly high IMF. So its surface tension is very sticky. That's why mosquitoes can land on water and not gasoline. Water boils at an incredibly high temperature based on its molar mass. It's a little bitty molecule, but it's got a really high boiling point because of the strong intermolecular forces. Okay, so IMFs are important. Biologically, our bodies depend on intermolecular forces. There's something called a membrane. For example, a cellular membrane. That's a membrane that goes on the outside of a cell and defines that cell as a body of water exclusive of the outside of the cell. Because membranes are very non-polar. Non-polar means very low IMF. So the water cannot get through. So our body's way of coping with this water issue, we're a big sack of water. How do we differentiate one part from another? IMF. Extremely important biologically. Okay. Now, what happens when we take something that has strong IMFs and put it in a solvent that's got strong IMFs? It dissolves really fast. Because the solvent IMF pulls apart the solutes. So when you take something like, what is this called? Methanol, throw that methanol in water, those two intermix very fast. Who has seen a bottle of vodka? Oh, gee, everyone's raising their hands. Can you tell the difference between the ethanol and the water? No. That's because ethanol's strong IMF, water's got strong IMF. So they become miscible in one another. They mix very, very well. Now we're going to find that the more carbons we add, the more and more non-polar it becomes, to the point of carbon number 7. If it's got 7 carbons or more, it's considered non-polar, even with the OH group. Even with the OH group. Because the other carbons will overtake the polarity of that OH group, and they will take over. Up until that point, though, it's a polar molecule. So 4 carbons long, polar. 5 carbons, polar. 6 carbons, polar. 7 carbons, non-polar. Non-polar. And that's because the IMFs of those carbons overtake the IMF of the OH group. We're going to find this is true throughout this course regarding one side of the molecule is polar, the other side is non-polar. Which dominates? Well, it depends how strong the non-polar group is and how strong the polar group is. Okay. Okay, so all the alcohols, primary, secondary, tertiary, at a much higher boiling point than their associated alkenes and alkenes. Now, we haven't talked about ethers yet. Ethers are going to come kind of in between. They don't have an H attached to the oxygen. They have another carbon attached. Okay. I want to talk about, before I get into reactions, and talk about ethers. And ethers are, where is the ether here? What ethers? We talked about phenols. All right, ethers. Ethers have got a COC. Doesn't matter how long the C's are, you can have 29 carbons on either side. If it's not, it's got an OTO, then it's an ether. Now we're gonna find in unit 2, we're gonna have a, instead of COC, we're gonna have an OCO. It's different. They act different. And that's the chemistry of carbs. It's the OCO. COC in the chemistry of ethers. Very different. Okay, there are two ways to name an ether. The IUPAC way and the common way. Now, if we look at here we go. 2 carbons on either side of that oxygen. So it's got a COC. That means it's an ether. So the common way of naming that would be diethyl ether. They don't have to be the same. They can be methyl ethyl ether. That's the common way. Who's heard of MEK as a solvent? Anyone? MEK stands for methyl ethyl ketone or methyl ether ether. So it's used a lot in paint industry. Okay, ethers can also be cyclic. We have COC, COC. And this is big time carb territory. Because we have furanoses and puranosis. So we have 6-membered carbs, 5-membered carbs. This is what fructose looks like. Fructose is a furanose. Glucose is furanose. Bottom line, they can be cyclic like all the others. Okay, IMFs for ethers. The IMFs for ethers are halfway between alcohols and alkanes. They're polar, but not as polar as alcohol. So if we were looking at so we've got an alkane, alkene, alcohol, ether. Okay, so the alcohol would have the highest. Propane, 3 carbon, the lowest. Everything else in between. Just figure ether is halfway between. Just as an approximation. Now, if you put an ether, automatically we have oxygen. Again, whenever you see oxygen, think IMFs. Strong IMFs. Now, because this dimethyl ether here, and no H attached to the O, it's not as strong as having an alcohol. So, strong, but not as strong. So because of that, they still can be dissolved in water because the oxygen, but not as easily because they aren't as strong. Another interesting kind of little side note is something called thiols. Because sulfur is underneath oxygen on the periodic table, its chemical characteristics are similar to oxygen. So if oxygen can form an OH, sulfur can form an SH. Similar problem. Not the same, but very similar. Now, this is a really important reaction because one of our amino acids is a thiol, cysteine. Thiols react with heavy metals like that. That's one of the reasons why heavy metals are so poisonous, is because your enzymes that have a cysteine amino acid in it die. They can't function as an enzyme anymore. So if they're in an important pathway, you're going to lose out. And also they're permanent. So heavy metal poisoning is very, very bad for the environment. Doesn't go away. We had a super site up in Tacoma. Remember the smelter there? Yeah, that was a super site because they used to smelter lead there. And that smoke coming out of the smelter went up and down the coast, all the way to Canada, all the way down to Oregon. So it became an EPA Superfund site. Big deal. They have signs when you get near the water. It says, do not eat bottom fish, like flounder. Because flounder go on the bottom. And where does lead go? Does it float? No, it sinks, right? So flounder tend to have more lead in it than other kinds of fish. Same with crab. It's becoming better, but it's still not good. So sulfur is really an important element in our bodies because it's incorporated into them. When those enzymes don't work, the pathway the enzyme is in also doesn't work. Okay. And this is what happens is we have a heavy metal. It attaches to two SHs and pins those together. There's a lot of research in the Tacoma Puget Sound area regarding enzymes that incorporate cysteine amino acid, because they use that to track how bad the pollution is. Everyone thinks the Northwest is so pristine. It has its challenges like every place else. Okay, and polyfunctional compounds have more than one functional group. Hence, the chemistry is harder, it's more complex. This is glucose, and then glucose in the ring formation, which is the most common way of seeing it. It also opens up a long string of alcohol. And the very end is an aldehyde. Aldehydes are very reactive. They react very, very easily. Okay, so we haven't touched upon reactions yet. So let's get into reactions. Now, if you took a snapshot of the flow chart I gave you, these are the reactions alcohols can undergo. We can take an OH off the alcohol and it forms an alkene or an ether depending on temperature. 140 versus 180. Also, we can oxidize alcohols depending on whether they're primary, secondary, tertiary. Can also reduce them, go the other way. In other words, if we want an alcohol, we can get it from an aldehyde or a ketone, going the other way. Okay, so this on top of the alkene reactions really adds quite a few possibilities. So let's do some simple reactions here to get us going. What I'm going to do, I'm going to do some simple reactions today. On Tuesday, I'm going to be really hitting hard on reactions. Because this is the last subunit in Unit 1. Unit 1's got alkanes, alkenes, and alcohol ethers. And there's a lot of reactions involved there. So let's take some simple reactions. Okay. What happens if I have let's say I have ethanol, and I threw it in a very hot vat of sulfuric acid. What's going to happen? Well, we're not oxidizing it. So that's not this route here. That's an oxidative route. What we're doing is we're heating it only in an acidic environment. So, acidic environment, heat, and it says alkene. Now, what happens in this reaction is that water comes off. Now, if you remember on Tuesday, we talked about when you add water to alkene, you create an alcohol. When you pull water out of an alcohol, you create an alkene. Now, I don't know if you remember, but on Tuesday I said alkenes are not very stable. That's why it naturally goes to the alcohol. If we're going the other way, kind of like an unnatural way, so we have to supply lots of energy. That's what this is. Lots of energy. Okay, so what happens now? We're going to pull off water. Water is H2O, as you know. So we have an OH here. And on an adjacent carbon, not the same carbon the OH is attached to, is there an H present? Yes, H is present. So here we have the water, H, H2O. So what happens is water's pulled off, leaving us a double bond. Of course, we've got to name it. This would be ethanol. This is going to be ethene. Now, looking at that reaction, you know that the OH is more stable than the alkene you make, because you had to put a whole bunch of energy into it. If the alkene was more stable, you wouldn't have to put any energy in. It would just go by itself. Which is what happens when you have an alkene and you dump in some water. You no longer have an alkene anymore because it usually goes to the alcohol. If you want the opposite to happen, you have to put lots of energy in. Okay, so that's your first alcohol reaction. Okay, what if we wanted to make let's make that. Well, it's an alcohol, right? Okay. The alcohol reactions. Now, when we look at this chart, there are arrows. The arrows are going to the product. If we reverse the arrows, it's going to go towards the reactants. So, in this case, if we add water to an alkene, we get an alcohol. We have to go against the arrow, though. So that means we're going to add an alkene to get the alcohol. So the alkene is the reactants, alcohol is the product side. So this is a product side. We want to make that. Okay, the reactant side, product side. Carbon backbone remains the same. 1, 2, 3, 4. So we have a 4-carbon backbone to start with. Now, if we look at the chart again here, when we add water and an acid across the double bond, we create an alcohol. So here's our alcohol. So our double bond has to be here. So when we add the OH and H, across that double bond, we end up with the OH. And we need an acid environment. So this is the first synthesis reaction you've done. We are synthesizing this alcohol on the right. So we'd say 1, 2, 3, 4. So it's going to be a 1 butanol, 1, 2, 3 methyl, 1 butanol. We're making that. Okay, and we make it from what? Well, we've got a similar alkene on the left. So we have 3-methyl-1-butene. We're gonna add some acid and water. I'm gonna create 3-methyl-1-butanol. Now, the problem with this reaction is we're gonna get a mixture. And on the test, if I asked you how to make this, you don't have to worry about a mixture. And we have to have a mixture problem if you're adding something to reactants, then you get a mixture. If I ask you how to create something, just tell me how you create it. Now, if we did this reaction, we get this. That would be the other product. And on either side of the double bond. Okay. We need to practice these a whole bunch. A whole bunch. And it's just a matter of what are you starting with, what are you ending with, what are the conditions? Name starting, name ending. All tests will have reactions on it. Okay, does everyone see how I got that? How I got that from this? Now that flow chart again, a lot of people ask me, do I have to memorize that? No. This guy, I'm going to give you that on the test. Okay. And there's a unit 2 version of this, which I'm going to be adding down here. It includes all of this. So the unit 2 version and unit 3 version, unit 4 version, there's no unit 5 version. Unit 5 is strictly biochem. Okay, so what I'd like to do is end here. And I'm going to pick up on Tuesday by doing a whole bunch of examples. Just to give you lots of practice. On your current dry lab, the last page is reaction. And I don't think there's harder than this one, there's definitely yeah. You're gonna have some practice on your dry lab as well. Okay, any questions? And this is typical, I never get questions. Unless I do things wrong, yeah. Huh? No, it'll be Thursday of next year.